This conference will now be recorded.
All right, all yours.
Okay, thanks, Bobby. I think that today we're going to just give everyone a quick update and a little snapshot on what we're doing with the ODSA bunch of wires product and project. One of the companies we work with and are working with on this is QuickLogic, which has already announced an FPGA solution, which will leverage die-to-die. And also with us is Comira, which is one of our partners, and their focus is on Ethernet. And they'll have a few slides that talk about how 800 gig can be easily transported over die-to-die links, whether they're UCIe and bench wires. So that they'll have a few slides that cover that. And then I'll end that with more on the interop side, because where we're seeing some issues and potentially how we can sort of help with adoption. Okay, so obviously the things that are driving chiplets, I think most people obviously know here, the promise of lower manufacturing costs, lower power, faster time to market, things like that. And I think it is delivering for closed systems from people like Apple using it, some of the switch companies have been using it, the FPGA companies have been doing it, the processor companies. Chiplets are definitely happening, but there are obviously some barriers to some of the open standards, and that's why we're all here as part of this series of meetings. And obviously ODSA is driving that, which is why we're participating. Just in a very simple, just stating the obvious, if you have a very large SoC, you split it into smaller bits, you get a lower cost. But obviously the cost, the only cost you really have is latency and power. So that's what's driving us as an IP vendor, is to try and get our latency as close to zero as we can, and get our power as low as we can. So that's essentially what's driving us. And we're leveraging obviously ODSA solutions, and we're really targeting 7/6 nanometer, although we did start with a 22 nanometer solution first. And we intend to support multiple bump pitches, including obviously 130 and 50 micron. Just talking quickly about FPGA solution that we're working with QuickLogic on. The idea is a pretty small little tile, which is essentially surrounded by die-to-die PHY. So you get a very low cost solution, a very low power solution, and there's no wasted power on I/O that an end customer may not use. And the whole idea is that this chiplet will be part of other chiplets within a package, right? So that's basically the premise here. And they'll talk about themselves when the Mao talks about their compiler and how the specific capabilities that they're developing. And the same thing applies to some of the large SoCs, but they're more driven by time to market. And so if you can reduce cost and get to market faster using proven chiplets, that's been the holy grail. But getting those chiplets developed is really the standard. So we need open standards, and we need multiple vendors, right? So I think this is where this is a challenge that the whole industry and we are facing together. From a Topus' standpoint, we have started with ODSA, and our focus is on trying to get our power as low as possible, and support multiple speeds from basically 4 gig up to 16 gig. And for our lower power solution, we're focusing on 4/8 gig and shorter links, without getting too specific. We are going to support a non-standard rate of 500 meg, primarily because we've seen some interest in clients want to go off package. I know that might be sacrilege here, but there is actually a need of actually going off chip occasionally. So that is something that we're working on. And from our standpoint, we are an IP company, and we obviously have SerDes IP, and we're also adding this year support for PCIe for Gen 5 and Gen 6. And then we really work with controller partners. We are developing with a partner PCIe Gen 5, PCIe Gen 6 controllers. And we obviously work with, on the Ethernet side, with Comira, and they'll talk about their solution a little bit later. And we're working with some other partners on JESD, which is now going to 64 gig SerDes in its next version, and USB 4. The next version is going to go to PAM3, so not just a traditional NRZ. So there's a lot of change coming in all of these standards, and even PCIe, which is just going to 64. They're now starting to talk about 128 gig SerDes, right? So we think that this change in the IOs is also going to be a driving factor for the chiplet space, and that's part of the reason why we're really involved in this, because it drives our business. In terms of the QuickLogic solution, it'll talk about how they compile everything, but their concept is basically a small tile with a bunch of connectivity around it, and then you can put, or a customer could put multiple of these within a single package, and they get a flatter cost curve, right? As opposed to the yield dropping off as the chips get bigger. And it's also easier to make it, fit a given customer's application. So we hope to be able to start designing with customers jointly by the fourth quarter this year, and this will be more of a delivered product sometime in 2023. So going to the next slide. So that's a sort of background on sort of what we're trying to enable with QuickLogic, right? An FPGA chiplet, and it could be coupled with an SoC or an ASIC, and potentially an IO chiplet either from us or through a partner. And we do see this aggregation continuing, although we all talk about disaggregation. So we're aggregating on the PC board, putting more junk into a single package, but that package isn't just a single chip, right? So it's going to be multiple chips. So that's basically the background of what we're doing. So I think Mao's going to say a few words about their compiler and their technology. And so Mao?
Sure. Thanks, Kash. So basically, we just wanted to talk about. Are you able to hear me?
Yeah, I can hear you. It's just the slide
okay,
was
cool. Yeah, no worries. So we just wanted to mention a little bit about how we actually create the embedded FPGA, and it's a little bit different from what some of the other eFPGA vendors out there. Well, first of all, we've actually been doing FPGAs for the past 30 years, so we have a lot of experience. We've actually been doing it the old way, as you can see it in the slides, which is custom design and go, piece by piece and go through that 10-month cycle to come up with one FPGA in a specific size, array size, and a specific process and foundry. Now we're actually moved into the new way. So we're actually using what we call the Australis IP generator. So users or customers goes through us, tells us kind of what size they want, what kind of trade-offs they want to make, whether it's power, performance, or area, and we can optimize the embedded FPGA block and then generate it for them as a hard macro. And that's what we provide. And I guess in this example, working with eTopus, roughly in a 200K lot, but we can provide more or less. It really depends on what the customer wants. Okay, can go to the next slide.
Yeah, so I just wanted to add, Mao, that
Yeah.
obviously you can migrate this to, let's say, a next generation process. And obviously we're designing a bunch of wires so that we can migrate it to another process. So even if our chiplet
Sure.
is in, let's say, 6 nanometer, we could move it to a different foundry, a different process. I'm trying to forward this. Okay, here we go. Sorry.
Yeah, very easily. Yeah, thank you.
Yeah, very
No
easily.
problem. So basically, just I wanted to summarize for what the Australis generator really gives us is the ability to customize that array size in any shape form per se. I mean, of course, there's some limitations, but basically, whether somebody wants a very small embedded FPGA or a very large one, that can be easily accomplished. We can move to any process foundry within a quarter of getting the standard cell and the PDK for that process. And the last thing that is very important is the tools for what is called a user tool. So like, for example, if you're used to using Xilinx, then you get something. You're used to Vivado. We provide something called Aurora, but many of we also provide a fully open source version that could be compatible with SimpliFlow. So that allows users who want to have full control of being able to get the source code of what goes into your embedded FPGA and have full control over that. So that's also a great advantage. And the tools do have full support from us in terms of being able to do the entire process of synthesis, place and route, and the final bitstream programming to the embedded FPGA. Okay, I think those are the slides I had. Cash,
Hey, just one question.
Yeah.
So,
Yes.
who makes the FPGA chiplet if you wanted one? Is it going to be QuickLogic or is going to be eTopus? Like, who makes the FPGA chiplet with the FPGA
Okay.
and it?
Yes, that's a great question. So the advantage for QuickLogic is that we're not just an IP vendor, and so we're actually have the entire operations, and we're able to actually make the devices. So to answer your question, for this ones, QuickLogic will be actually producing them. Does that answer your question? Yeah.
Yeah,
Yeah, I was
Go
just
ahead,
going to
please.
say, and we may have a customer that wants it as IP, right? The IP could be GDS2, and we'll work together on our side to deliver that too. So we're really trying to be customer specific or customer sensitive, and have an open solution, if that makes sense. So the customer will be able to buy whatever they want, right? So it could be a large semiconductor company, or it could be a smaller one and they want finished goods, and we're an IP company. We're not going to support that. QuickLogic has the infrastructure to support that, which is very important.
So I guess the part I'm trying to sort of square in my head is, if you're building a chiplet, why is process portability very important? I'm asking, not complaining. Just if you're going to build a chiplet.
Okay. Yeah. So the one that we're building right now, that's going to be on 6 nanometer, right? And that's working with some specific customers, and there will be devices that we would produce, and as Cash mentioned, we can sell finished goods or we could sell the IP itself. However, for us, QuickLogic, we have this capability, and we know that what we have noticed that in this several years, one size does not fit all. So if somebody else wants something different, then we can also support it. And whether it's from just a size difference in terms of the FPGA itself, or they want to have it in a different process, different foundry. So that's why I mentioned that.
Yeah, I think
That makes sense.
it's actually critical, Bapi, because the customer may want the FPGA portion for smaller die or customized to their needs, but they could also use the standard IO chiplets in the 6 nanometer example. And the other thing is, in a lot of applications, a customer does an SoC, then they have an FPGA block for flexibility. So they can also deploy that. So they would want potentially that FPGA in their process, for example, but they may want the chiplet and off the chiplet, right? Or they might want a standard chiplet that's off the shelf. So we're trying to make sure that we can cover essentially what all the different options that the customer would like.
Got it. Okay. And there's one last question. I'm sorry.
Sorry.
If you make the chiplet, and does that mean you will also own the packaging, the testing of the chiplet, and the delivering known good die, etc., or how is that somebody else downstream who does that?
This is where we'll talk about known good die and the other issues that we all face a little later. But
Okay.
Yes. Okay. So we're going to talk about Comira, who we've done some press with already in terms of working with them. They're just as a quick intro. I've actually competed with them in a previous life into some very large tier 1 accounts. They've been around for a long time. Their IP is well proven at major tier 1 networking companies, and we're very pleased that they're a partner of ours in the chiplet space. And I'd like to have Aaron say a few words about their specific solution that they're developing and working with us on. Aaron?
Thank you. To start off, I'll give a brief overview of what the UMAC is. Essentially, it's an integrated Ethernet MAC PCS and FEC. The UMAC receives packets from the core logic via a pair of UCIe and bunch of wires 2 translation layers and performs the operations necessary to transmit the data to a link partner over multiple SerDes lanes. Similarly, it performs the reverse operations in the receive path. So in the diagram here, the UMAC would be the green boxes in the middle. A UMAC can be constructed with various options. The example that we give here, it's a 800G UMAC with an aggregate bandwidth, an aggregate bandwidth of 800G UMAC. It can be subdivided into multiple independent channels that each operate at its lower speeds in arbitrary mixed modes. So there's a few modes given there. We support basically every standard Ethernet rate. The UMAC may also include the Reed-Solomon and Firecode FECs, high accuracy timestamping, auto negotiation, flow control, as well as an integrated statistics capture module that tracks packet and data path information. We see several benefits of including the MAC and the PCS together on a chiplet. We have a few listed here. It allows for timely flow control termination and response. It gives a SerDes agnostic interface to the core, which means a chiplet using 8 100G SerDes to support 800G could be easily swapped out for one that uses 1650G instead. Having the MAC framing logic as near as possible to the SerDes allows for high accuracy timestamping. And the UCIe and bunch of wires 2 speed can scale with the aggregate SerDes bandwidth, which means you can take an 800G chiplet and you can easily swap it out with a 400G chiplet just by reducing the interface speed. And finally, the implementation and design risk are reduced by including the MAC, PCS, and SerDes in the same proven chiplet. If you go to the next slide, please.
Yep.
So high accuracy timestamping is not applicable to every use case, but it's a function that we're seeing a lot of increasing demand for, and it presents a unique set of challenges that we must consider when we're looking at this. So PTP timestamps must be generated for the time that a packet is seen at the MDI. However, one-step timestamps must be inserted into egress packets before the MAC framing and all of the PCS functions are performed. This means that the delay that the packet will experience as it travels through the data path must be predicted and accounted for. To meet the requirement for PTP class D, the timestamp accuracy has to be within 5 nanoseconds, so it's very tight. There are several functions in the MAC, PCS, and FEC that will reduce the accuracy if we don't account for them, including the flow control, the alignment marker insertion, IFG compensation, and the PCS lane distribution. And by keeping the timestamp insertion point and each of these contributors of the delay variation together on the same chiplet, it makes the UMAC able to use a patented technology for generating timestamps that do meet that Class D requirement. If you could go to the next slide.
Hey, what does the PTP requirement mean for if the EMAC is a chiplet? I mean, what's the impact on it being a chiplet?
So basically, the main point there is the point at which you insert the timestamps into the packet, keeping it on the same chiplet as the time that needs to be represented that you're inserting makes it much easier to monitor that delay variation. So if it's separated onto the other side of that interface, you now have another contributor to that delay variation that needs to be accounted for in some way.
Okay.
Yeah, Bobby, it needs to be really tightly coupled, as Aaron is saying, right? So you can't just have it on the SoC and just have the SerDes sitting, somewhere in the ether on a chiplet, right? So the Mac PCS needs to be very close. And as he has said, that as real time sort of Ethernet is becoming more and more critical, right? Particularly things like 5G and other networking. That's where the timestamping and the precision timestamping becomes more critical. So the key thing I think we're saying is that there's a lot of complexity here, and also this stuff's running at what 1.6 gig, right, Aaron? So
That's right. Yes.
it's challenging even from a design implementation standpoint, because you may want a whole bunch of ports. So having it on proven on a chiplet, you save quite a bit by just buying an off-the-shelf chiplet eventually, right? Because it's proven implementation, your design process is faster, design risk is reduced. You don't pay the IP fee, obviously. So there are a number of advantages to SoC companies where they sort of focus on what they do best. And this applies to PCIe and some of the other newer protocols too. And let's say that Etopus's chiplet somebody doesn't like, they could then proceed and drop that and drop somebody else's chiplet in there. So hopefully later on it'll be multi-vendor. And then secondly, as he's saying, I know that they're already working on beyond 800 gig, right? As people go to 1.6T, so you can design your SoC so that you've got enough ports, and then you can pop in, a higher speed version. And as Aaron already mentioned, you could also, with the same interface, do 400 gig. So if you're trying to do a differentiated product, you could have, a 400 gig version, an 800 gig version, and then in the future a 1.6T version. So there's a lot of flexibility that you get by using an external chiplet, and I think that's part of the reasons why Ethernet chiplets, right, are now being used even within the fixed function FPGA. So if you look at what Intel has shown, they show an external Ethernet chiplet, for example, right, or an external PCIe chiplet. Yeah.
I have one question regarding the latency. I think it's on the previous page you mentioned about P2P Class D that require like a 5 nanosecond latency. So I just want to know what's
precision, it's precision, not latency.
Right. Yeah. That's a 5 nanosecond accuracy for the timestamps.
Oh, the accuracy. And based on like 800 gig, this link layer like latency, how much it's going to be in general? Just want to
the data path latency for our implementation,
yeah.
it's roughly 100 nanoseconds.
100 nanosecond. Okay, thank you. Yeah, just wanted to know that.
Okay, and then obviously the other thing, Aaron, just want to make sure you highlight is the need for a sideband, right? So
yes.
Yeah.
Okay, so I can go through this slide here quickly. So this diagram gives some more detail of what the UCI and Bunch-of-Wires 2 translation there looks like. The interface that we're using here is based on the advanced package with 64 lanes operating at 16 gigatransfers per second to support 800G. or it can be also used in 8 gigatransfers per second for 400G. 56 of those lanes are dedicated to the packet data, with 8 of the lanes allocated to the packet sideband information, such as the SOF, DOF, the frame status, per frame settings, as well as a channel identifier to run the interface in TDM mode, which would support running multiple channels simultaneously. And then the register and interrupt accesses would be running through the UCI and bunch of wires 2 sideband path. And finally, because the interface operates slightly over the required Ethernet speed, the rate would be modulated through a credit system that is passed through the 8 lanes not occupied by the data.
Right. Okay. Aaron, thank you. So now we're going to talk about a little bit about more of an open discussion where we can share some of the issues that we see. So I think one of the issues that we've seen is that the current, as somebody new to a bunch of wires, frankly, there are some limitations with the current standard. So we are looking internally at expanding that to a 64 link solution with maybe some sideband and maybe some redundancy. And I know that the team at ODSA is also looking into sideband and redundancy. So I think that this is just something that's necessary, and we'll all be sort of working together on that. On the packaging solution side, obviously everybody started with 130 micron pitch. We're now seeing the 50 micron interest, and as well as even a very advanced solution that some people are doing with much tighter pitches. But it is sort of important that there is some side channel support to ease chiplet deployment, which the current BOW standard doesn't support, and some of the other competing ones do. So we'll be adding it, whether it's standard or non-standard, but it is something that the folks do need to be aware of. The other thing is, things like testability, as we go to things like known good die, is the die still good before it's put in the package, also monitoring the health of the chips. So it's and maybe things like calibration. I think that this is an area that's kind of weak, and we're sort of putting some effort and energy into this area, because it is because the moment you actually look at it from a customer standpoint, they don't really care how you do it, but they just want to make sure that the damn thing works, and and if something breaks, that they can figure out what happened and why, right? So so things like redundancy to support advanced packaging, even potentially fixing field failures. So this is not something where we have all the answers, but I think that some flexibility needs to be built into the standards as we move forward. And then I think that the the whole reason why we're here is because of the goal of an open, interoperable system, but the infrastructure right now to really see how you can test and interoperate is sort of somewhat limited, right? So we'll have some slides on what we'd like to do and get feedback from the teams. The other thing is that security is not really well addressed. So when you have multiple chiplets within a package, so we've talked to our partner QuickLogic, and they actually have a root of trust solution within their FPGA with another partner, and so you could see this being potentially extended across multiple chiplets, and I think that may be of value to large system vendor customers, because this is something that they're interested in, not just getting a lower cost solution in a package, but also is there a way to really secure this? I've already mentioned that we've seen a need to drive off package, and we don't need to get too much more into that. So what we're sort of putting together is potentially something that looks like this, right? Because we are not just going to support one pump platform. So we may do something where,
Vikash,
sorry.
I think there's a bunch of discussion to be had about the previous slide, probably in this meeting and in the Bow meeting. Do you want to do this now or after you've gone through all your slides? What's your preference?
Yeah, let's do the slow slide so at least we get everything out there, and then we're not looking
Okay.
for all the answers today, but at least we're giving you our perspective. I'm giving you my perspective, right? And then
Yeah, hey, I'm trying to figure
yeah,
out I want to understand this in more detail. So yeah, maybe when we come back to this slide, I like this good summary slide, and
okay.
after you're done, we come back to it.
Yeah. So one potential way that we could do this is obviously once QuickLogic's FPGA chiplet is out, we can put a couple of those within a package. And as we develop our chiplets with our partners, we may have one that's dedicated. But our idea is to also enable this for other people, right? So let's say if somebody has a different chiplet developed, they could leverage this and leverage the FPGA to, for example, play with redundancy or play with different link controller mechanisms. So we're wanting this to be more of an open thing rather than a closed solution, if that makes sense. So, and it could even be, a QuickLogic FPGA, and let's say that vendor B comes up with an FPGA chiplet, right? It would, from an end customer standpoint, you want to make sure that they can also interoperate, right? And so within that package, it could just be one of each, or it could just be a vendor SoC. So these are just showing some examples. It could be somebody else's FPGA and also an SoC that our customer is doing, and they want to interoperate with the FPGA as well as test against whatever third-party chiplets exist, right? So we're going to be working towards this. Obviously, if we can get more interest, we'd certainly want to leverage any help and support to increase the openness of this type of solution, right? And what I was going to end with was, I think that there's a huge, obviously the return promise is massive, but people need an easier path, right, to deploy and develop chiplets. And I think that, because I'm in sales, I always try and not just wear my own hat, but I'll wear the hat of my customer. So if I wear the hat of somebody with a great idea and they want to develop a chiplet for this massive new market, it's kind of difficult, right? So our plan is to offer our PHY, our IP to developers to get the ecosystem going, sort of just on a royalty basis. And even if our IP is free, they've got to, place and route the chip. They've got to do that. We may be able to help in some of that. But the other thing is, how do you now take that chiplet to market? And we really would like to see some thought and effort put into this, so that if somebody's got some genius idea, then they don't have to raise $20 million to do something, right? So or more. And so if there's some way of sharing manufacturing, so even if your cost is higher, yes, it's great you can do an MPW run, but the moment you've got to try and sell that chiplet, you're faced with a number of problems, right? There's no market, there's no exchange, or eventually there will be. Maybe it's 10 years away, maybe it's 3 years away, but we have to cross that chasm of making it real. And so these were some ideas of how do we enable an ecosystem. We'll do our part, right? But we're certainly not going to be able to do all this, right? So for other companies that want to develop these items. So I was going to leave it at that. That's basically my slides.
Okay. These are very nice. Does anybody have any questions? I don't want to monopolize the conversation. Otherwise, I think I want to go back to your problem list of challenges Actually, all three are kind of lists of challenges that are worth a shot at. Anybody else with any questions?
Just a simple one. You kept on mentioning BOW2. What is that?
That's going beyond the current bunch of wire. I think we've just got BOW, the basic bunch of wires specs completed, right?
Okay, Cash,
And
you want me to comment?
sorry?
I was just asking, do you want me to comment on that one?
Yeah, please, Alan, please.
Yeah, so we've actually had the BOW 1.0 sort of spec from a technical standpoint done for a number of months already. So the working group for almost about 6 months now, I'd say, has actually been sort of making good progress on defining, what we would call the next generation of BOW. I don't think we've officially come up with a name, by the way, but for lack of a better one, sure, we can call it BOW 2.0. But it includes a number of specific features, enhancements, etc. That I'm happy to go through in more detail. But a number of them are actually sort of addressing things that Cash had mentioned in the challenges slide. Did that
Okay,
answer
that's
the
what I
question?
thought. But
Yeah.
I thought that was there's already a brand that because we are going to announce BOW1. And I just want to make sure that we are all aligned on the naming convention. That's all.
Yeah. No,
Oh, yeah,
absolutely.
it's both.
Yeah, no, yeah, that's a good point. I just use internally, I'm using Bow 2.0. Okay, so I don't know. I'm not very innovative. Maybe maybe we should call it the ultimate, the universal bow or something. So to excite more people. I don't know. Whatever.
Yeah, no, we'll dedicate a meeting to coming up with a naming.
Okay.
Well,
That's
I
what
think
we.
the one sense I'm getting, Tony and Kash, is that this seems to be really focused on advanced packaging, and that's where you're seeing advanced packaging and sort of coexisting with UCIe. So that's pretty exciting, from what I can see.
Well, I think there is yeah. So I think that there's two applications, right? The standard bow is a really good fit for if you're doing a smaller die and not necessarily in the high performance arena, right? But the moment you go higher performance, you really have no choice but to go advanced packaging, and it's
Can you
the
go
only,
back to that slide of yours, that list? I really like that list.
Yeah,
Okay.
Cash, I can, we can have a technical debate on that last piece, but that's a different story.
So by sideband, you mean? Would you mind elaborating on what you mean by a sideband?
yeah. So for example, if you look at the way the other standard has implemented, and I'm not saying we are going to implement it the same way, but they do have some signaling required to manage the data flow, right? So right now we have 16 bits of data running through, and then we have these two spare bits that most people don't know what to do with. One's called FEC and the other is called aux, right? So if you just take 16 plus 2 and looking at it simplistically, if you go 4x, so in the same area you go to a 50 micron bump pitch, you end up with 64 links, and you get roughly 8. Those two go to 8. So 8 seems like a reasonable number for sideband. And I'm not trying to say exactly what it is. In fact, I know Elad and is going to be leading that conversation. And the other thing with advanced packaging is the need for redundancy, right? And
So
in our
hold that
example with our example on the 800 gig, you saw the need for sideband signaling, right? So and the other part of this was with advanced packaging, redundancy is also an option. It is an issue, right? So right now we don't address that in the ODSA solution. The UCIe obviously does address that in theirs, right? So we do have to address redundancy And there may be some other things that need to be addressed, like testability and validating the health or calibrating the links. So there is some need for some management links, and those links don't necessarily need to be at the highest speed. They could be. So this is something that as you go to higher performance, and frankly, this is probably going to be the sweet, in my opinion, at least. Now we go to opinion. That the high performance is what's going to drive this, right? So it is driving chiplets right now. Because if you're doing a smaller chip and it's in many millions of units, then you may be better off with that single chip solution, right? So that's just my opinion.
So you're essentially saying, if I understand you correctly, you prefer an out-of-band or sideband control mechanism for the link layer. That's where your thinking's going. I'm not complaining. I'm asking in terms of this.
Yeah,
this is my
I
understanding
think that I think that it's not just yeah. Without getting into too much of the specifics, certainly for the link layer functionality, having some sideband is very desirable.
So
But
sort of a
ignoring the
real-time
link
sideband.
layer,
Okay.
the link layer, if you're sending, Ethernet traffic, you need a sideband. You got no choice, right? However you configure it, right? Or if you're going to be doing PCIe, you're going to need to control that data, right? So I think the current focus has been more on just sending the data across the links, and now it's got to meet the popular protocols.
Okay. So I just want to make sure I go through the list here. So then on the three packaging options you have, the 120 to 130, 40 to 55, and the 20 to 25. For which of those do you think redundancy is important? Again, none of these are complaints again, because this is a wonderful list. Like, are you thinking like redundancy is essential for 20 to 25, or you need it for the other two as well?
I think you need it for 40 to 55 as well.
Okay.
That's my opinion. Ask Gilad. He's more into this, I'm sure.
Okay, but fundamentally at the right side of that scale, we need redundancy basically.
Yeah, and obviously the larger the number of links, the more likely that you're likely to have a failure too, right? So
right. Okay. So I think what I'm seeing is an interesting list of things to do for Bo for advanced packaging, and I think that we're doing, or the group is doing a bunch of these for advanced packaging in the sort of next rev. What is that the third line from the bottom? Would you mind elaborating on that? Planned interoperability.
The interoperability?
Yeah.
Yeah. So how do you let's say test your chiplet or your interface or your link mechanism, right? Right now, I mean, I know that we're doing this test chip, not a test chip, but this test board, right, for interoperability, and it has the is it a D-Matrix's chip and Elad's chip, right? Blue Cheetah's chip on there, right?
Right.
So it's looking at different lengths and things like that, but how do you interop one chiplet with another chiplet? And this is where I was getting to with the interposers and looking at how to test different ones using potentially those FPGAs, sending data through and looking at interfaces and things like that. So that's basically what I'm talking about. So basically, this sort of platform, right? So this could be an ODSA, promoted platform in some sense, where you have, in fact, I know test people who are doing this, right? They have, they use FPGAs to load up the data and they blast it through, into memory, and then that goes into the device, and then they look at data back and make sure everything works.
So a reference gold platform, a gold reference that somebody can access easily when they make their own board chip.
Yeah, Yeah.
Okay.
So let's say that I've now developed a chiplet, and it's not eTopus and it's not QuickLogic. You could pop your device onto here, for example, right, and test it with this FPGA or a different vendor's FPGA. I mean, so I think that there needs to be some effort put into this where you don't have to develop the whole test infrastructure. You can just change the interposer in some way or whatever, right? So this will involve and would involve partnerships with different people to enable this if we want to make this an open. But I think that something like this needs to be done.
Got it. Okay. So I have three things that I'm taking in the notes. One is redundancy for advanced packaging, a reference gold platform for interoperability tests, and a preference for a sideband interface
And
for the link layer.
redundancy. Yeah.
I have redundancy as number one for advanced packaging, right? That's what.
Okay.
Hey, one
Okay.
question. Your bullet testability and institute ongoing health, is that does it mean qualifying, using the term qualifying the chiplet for certain process technology? I mean, like in the IP case, right? IP, you always do silicon qualification on a certain process, right? So
No, in
does
situ
it mean,
means that yeah. Hi, Tony. Sorry. Yeah, in situ means when it's actually deployed, potentially.
okay, but how do you,
So
I mean,
monitoring.
okay, so
You're talking about link drift in the field, right?
yeah,
Whatever
or,
happens in the field, the link goes down, something goes wrong,
oh,
monitoring
I
that,
see.
being able to respond to that in some way, either give a notification to some system or bypassing that in some way. I think that because you're starting to put a very complex system within a package, right?
Right.
And failure is failure is a field failure is very, very expensive, and debugging that might be very, very difficult too. So so some thought needs to be put into that for sure.
I see. So that is to say, once the chiplets has been deployed, that the ongoing health is a challenge, right? That's what you meant.
Right. So there's two issues, as you know, right? One is the known die good, and then is it good once it's put in the package, right? And then assuming everything works, then what happens if something goes wrong in the field, right? So those are the we need to sort of look at this somewhat holistically.
I see. Yeah, because my
Do you-
question is a little bit a few steps before that. Is that when might be it's a part of your no good die, right? So how are you going to qualify a chiplet? Because I kind of see the chiplets is the next generation of IP, right? In a sense, you elevate IP into chiplets, and for IP, there's a pretty much acceptable way that you still can qualify an IP for a certain process. What are your thoughts about qualifying the chiplets to become the no good die?
Yeah, you still have to do that, just like you qualify IP. You have to run different lots. You're going to have to do all the corners, and just like you would with IP, right? So you're going to have to qualify your device, your chiplet device. That I think kind of goes without saying. But once you've qualified it, you still have the ongoing issue of actually making sure that you know that it's good, and you can do something about it if something goes wrong.
So
But to your point, you have to go through a full qual. You can't get out of doing a qual in the classic sense, for sure.
and one last thing, do you see security as a PHY issue or as a chiplet issue?
I think security is becoming a bigger and bigger issue, and if you talk to some of the data center people, I mean, they're concerned about it. Obviously, there are other markets that are very sensitive too. So
No, so I agree with that. I think my question is that something that the PHY spec addresses, or is it something that there's really it's a chiplet that as a whole that needs to be
I think the chiplet as a whole, for sure. Yeah.
Okay, so it's not something a PHY spec alone, just the PHY trusting its other compatriot on the other side is.
Right.
Because
Yeah.
I'm trying
So
to
having,
map it to, is it a bow issue or a chiplet issue is sort of my
but
question.
it could be something that's being managed or helped through these side channels, right? So,
Got it. Okay. Thank you. This is really nice.
okay. Well,
Thanks
thanks
for making the
everyone.
time.
I appreciate everyone's attention and help.
And hopefully you can bring these to your guys can bring these to the bow and bow test chip meetings and
I'm meeting out as a small company, but yeah, we're trying to give as much resources as we can to try to help and attend and be helpful. And thank God for Elad. So he's really driving this. I think without him there wouldn't be much going on. All right, thank you. Thanks everyone. Bye.
Thanks. Any questions for Kash?
Okay, thanks everyone. Thanks, Cash.
Thank you.
Thank you, Cash, Ken, Mao, and Aaron.
Well, thanks, Aaron. Thanks, Aaron, as well, and Mao. And no meeting next week on 7/8. It's Srijit from Intel. So have a good 4th of July and have a good weekend, everyone.
Okay, thanks, guys.
Thank
You
you.
too.
Bye.
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 Thanks. Bye. Thank you.